North American Aviation Test Facility, 1944. The P-51 Mustang already ruled the skies at 430 miles per hour. But Charles Sisk, a quiet engineer from Aeroproducts, was about to change everything people believed about propellers. The aviation expert was certain of one thing: the Hamilton Standard's thick, heavy propeller was the only one strong enough for the Mustang's extreme demands. Anything lighter, they thought, would snap under stress. Then Sisk introduced his design: thin, lightweight blades that looked far too fragile compared to the industry norm. The military called it too delicate for war. Senior engineers dismissed it as a rookie's mistake. Even test pilots doubted it could survive a single hard maneuver. Yet, on that first test flight, something incredible happened. The Mustang didn't just fly faster, it transformed into an entirely new machine. Radio chatter filled with disbelief as it reached speeds no piston fighter had ever seen. The propeller that everyone said would fail had turned America's top fighter into a deadly surprise the enemy could never anticipate. A cool morning mist hung over the North American Aviation Factory in Englewood, California, as Charles Sisk stepped into the engineering bay on October 15, 1944. The sound of riveting guns and roaring engines filled the air, but his focus was fixed on a wooden crate that had arrived overnight from his Aeroproducts workshop. Inside was a result of 4 months of tireless work, a propeller design that could either redefine fighter aviation or destroy his career completely. Sisk was never like the others. While his colleagues at Aeroproducts preferred small, safe improvements, he questioned the very foundations of aircraft design. The Hamilton Standard propeller fitted on every P-51 Mustang was a masterpiece of 1930s engineering. Thick, strong blades built to take massive punishment and deliver steady performance. But Sisk saw flaws where others saw perfection. Its heavy build caused rotational drag and limited engine responsiveness. It also added weight that reduced the aircraft's overall agility. Through endless nights of calculations and stress tests, he developed an alternative: thin airfoil blades designed to cut through the air with less resistance. Their reduced mass would allow faster rotation and quicker throttle response. Most daringly, he replaced Hamilton's complex variable pitch mechanism with a simpler, lighter version that still gave pilots full control. The reaction from North American senior engineers was predictably doubtful. Edgar Schmude, the brilliant Austrian-born designer behind the original Mustang, studied Sisk's blueprints like a surgeon reading X-rays. "Charles," he finally said, his accent still thick after years in America, "these blades look like they belong on a racing boat, not a fighter. How can they survive combat?" The skepticism spread quickly. When news of a new propeller reached Wright Field in Ohio, the Army Air Force's Engineering Command reacted with alarm. Colonel Mark Bradley, the officer overseeing Mustang development, sent a curt telegram criticizing the risk of testing unproven propeller technology while American pilots were dying over Europe. "The Hamilton Standard works," Bradley wrote. "Our boys need reliability, not innovation." But Sisk gained an unexpected supporter in Major General James Doolittle, the hero of the Tokyo raid. Doolittle knew that small improvements wouldn't be enough to maintain air superiority against Germany's advancing fighters. Visiting the North American plant in September, he spent nearly 2 hours reviewing Sisk's design and listening carefully to his reasoning. "Young man," Doolittle said before leaving, "I've learned that the biggest risks often bring the biggest rewards. If you believe this propeller can make our Mustangs faster, I want to see it fly." A standard P-51D was selected as a test plane, modified to carry the new propeller. Chief Test Pilot Robert White accepted the assignment professionally, but had serious doubts about the propeller's strength. During his pre-flight inspection on October 20th, White carefully checked the hub and blade fitting for any sign of weakness. "She looks fine on the ground," he told Sisk, "but looks can lie when you're pulling 6Gs in a combat tone." The first flight lasted only 30 minutes, with White keeping the Mustang within safe limits as he tested its performance. The propeller's basic performance proved solid. When White taxied the Mustang back to the ramp, his initial report was cautiously positive. The propeller operated smoothly across all flight conditions, showing no vibration or abnormal behavior. Engine response felt sharper than with a standard Hamilton setup, though White warned that more testing would be needed to confirm any real performance gains. In the following weeks, the test program expanded to include high-speed trials at multiple altitudes. That's when the Aeroproduct propeller's true power began to reveal itself. At 25,000 feet, the modified Mustang consistently reached speeds over 460 miles per hour, a major jump from the standard model's 430 miles per hour top speed. Even more impressive were its improved climb rates and acceleration, qualities that could make a critical difference in combat. The real breakthrough came during a high-altitude test on November 3rd. White pushed the aircraft to its limits, gradually increasing power while keeping a close eye on engine heat and propeller behavior. At full power, the airspeed indicator passed 470 miles per hour, then 480, finally leveling off at 487 miles per hour. No piston engine fighter had ever reached such speed in level flight. When White landed, he sat silently in the cockpit for several minutes, realizing what had just happened. The fragile-looking propeller that everyone had dismissed had turned the Mustang into the fastest piston fighter in the world. As the ground crew surrounded the plane for inspection, White couldn't shake the sense that he had just witnessed history. Sisk heard about the successful flight while working late, perfecting drawings for more prototypes. The phone call from North American's chief engineer was brief but thrilling. "Charles, I don't know how you did it, but that propeller of yours just made our plane fly like nothing before. We need to discuss production right away." Still, questions lingered about durability. The same lightweight structure that gave it its speed also defied traditional design logic. Could the thin blades handle combat stress? Would the simpler pitch system remain reliable in harsh conditions? And most importantly, would pilots trust a propeller that looked so delicate compared to the rugged Hamilton standard they knew? Those doubts were soon put to the test. On November 8, 1944, a telegram arrived from Wright Field, echoing the skepticism that had long haunted bold innovations. Colonel Mark Bradley's message was blunt. Aeroproduct propeller results seemed too good to be true. Suspend all tests pending full structural analysis. Cannot risk pilots' lives on unproven technology. The words hit Sisk hard as he read them in Schmud's office, surrounded by charts and flight data that told a completely different story. Schmud set the telegram down and looked at him calmly. "Charles, you knew this would happen. Every revolutionary idea reaches this point, when the old guard tries to stop it before it proves itself." He gestured toward the piles of data from 2 weeks of intense testing. "But now we have proof, real numbers that speak louder than fear." The data was indeed convincing, but Sisk understood why Wright Field was cautious. The Army Air Forces had learned a bitter lesson from rushed innovation. Early P-38 Lightnings had deadly compressibility issues, and the first P-47 Thunderbolt suffered engine failures due to hasty development. With that history, Sisk's radical propeller was exactly the kind of untested design that military leaders distrusted. Pressure mounted when General Henry Hap Arnold joined a conference call with North American executives. His voice, firm and commanding, came through the speakerphone. "Gentlemen, I respect innovation as much as anyone, but we're in the middle of a war. Our pilots need reliability, not experiments that might fail when lives are on the line." But Arnold's worries weren't just about safety. Intelligence from Europe showed that German engineers were developing new fighters that could challenge Allied air dominance. The Messerschmitt Me-262 jet fighter, though still rare, represented a massive leap in performance that could threaten the Allies' advantage if deployed in large numbers. Against this backdrop, small upgrade to existing aircraft no longer seemed enough to preserve the technological advantage American pilots had enjoyed through 1944. Sisk now stood between two powerful forces, the military's cautious bureaucracy and the engineer's hunger for innovation, as he worked to address Wright Field concerns about structural strength. The lightweight build that made his propeller so fast also raised valid doubts about how it would handle fatigue under real combat stress. Standard propellers were tested in controlled labs, but those trials could never fully mimic the punishing conditions of aerial combat. High G turns, rapid throttle changes, and sudden shifts in altitude placed unpredictable loads on blades that no formula could accurately predict. The solution came from an unlikely ally, test pilot Robert White, who had once doubted the Aeroproducts design. He suggested running extreme stress tests that would push the propeller far beyond its normal limits. "If these blades are going to fail," White told Sisk in the hangar, "I'd rather they fail now, on my watch, not in a dogfight over Germany." His plan involved aggressive maneuvers meant to push the aircraft, engine, and propeller to their breaking points. High-speed dives followed by brutal pullouts would test the blade's strength against centrifugal force. Rapid power shifts would challenge the pitch mechanism under heavy loads. Long high-altitude flights would expose the metal to temperature swings and fatigue. The first of these tests began on November 15th. White took the modified P-51D to 30,000 feet and dove steeply, letting the aircraft exceed its normal speed limits before pulling out hard. The Aeroproduct propeller endured it without a hint of damage. Over the next week, he ran more extreme trials, high G-turns at full power, rapid climbs to thin air, and sustained high-speed flight at sea level, where the thick atmosphere placed the greatest strain on the blades. Through every punishing run, Sisk monitored blade stress, hub heat, and vibration using specialized instruments. The results astonished everyone. Not only did the lightweight propeller survive, it performed better than the Hamilton standard model in every comparable test. Its lower inertia gave faster throttle response, while the refined blade shape kept efficiency high across all conditions. The turning point came on November 22nd during a direct comparison flight. White flew two identical P-51DS, one with a Hamilton standard propeller, the other with Sisk's Aeroproducts design, through the same maneuvers. The outcome was unmistakable. The Aeroproducts-equipped Mustang climbed faster, accelerated harder, and reached a top speed of 489 miles per hour at its ideal altitude, nearly 60 miles per hour faster than the standard version. When Wright Field received the detailed test data and gun camera footage documenting the flights, the response shifted overnight. Colonel Bradley's next telegram was short but clear, test data convincing. Recommend immediate expansion of evaluation program. When can you supply more prototypes for operational trials? For Sisk, the long-awaited validation had finally arrived, but it also brought new pressure. Succeeding in controlled tests was one thing. Proving the propeller's worth in real combat would be something else entirely. As orders came in for operational trial units, Sisk sensed that his defining moment was approaching fast. The war wasn't waiting, and American pilots needed every edge they could get as the enemy fought harder with each passing month. On December 3, 1944, the first operational test aircraft rolled out of North American Aviation's modification hangar, marked with the insignia of the Army Air Force's Flight Test Center, and carrying a secret innovation that would soon change the course of aerial warfare. Charles stood beside them. The pilot's experience and strength. White fought the controls as the Mustang strained against the forces threatening to drag it into an uncontrollable descent. With calm precision, he eased back the throttle, deployed slight trim adjustments, and slowly pulled the nose upward. The aircraft responded, shuddering violently before leveling out at 12,000 feet. When he finally stabilized, sweat covered his face despite the cockpit's cold altitude air. For a few tense moments, the world's fastest Mustang had brushed the limits of what piston-engine flight could endure. From the ground, engineers and officers of the test control station exhaled in relief as telemetry confirmed recovery. The P-51H had touched the edge of 500 miles per hour, territory previously reserved for experimental rocket aircraft, and survived intact. When White taxied back to the ramp, a crowd of mechanics, engineers, and senior officers surrounded the aircraft. The propeller, still gleaming in the sunlight, showed no signs of stress or damage despite the punishing run. As he climbed down from the cockpit, White removed his flight helmet and shook his head with a grin. "Charles," he said, "you've built a monster. She just wants to go faster." Sisk allowed himself a rare smile. For months he had defended his design against skeptics who claimed it would never survive real flight. Now, standing beside the gleaming P-51H, he had proof that his creation had not only survived, it had redefined the Mustang's limits. The post-flight inspection confirmed the aircraft's structural integrity. Minor heat discoloration on the blade tips indicated thermal stress, but no cracks or deformation were found. Sisk took careful notes, already planning design refinements to improve heat dissipation and dampen vibration at high speeds. He knew that this success, while historic, marked only the beginning. Pushing technology this far meant confronting new problems as fast as they appeared. That evening, the test data were compiled and reviewed in North American Aviation's engineering offices. The numbers were beyond anything the team had imagined. Acceleration rates 15% higher than previous Mustangs, climb performance unmatched by any Allied fighter, and sustained speeds nearing 490 miles per hour. For all practical purposes, Sisk's lightweight Aeroproduct propeller had turned the P-51 into the ultimate piston engine aircraft. Still, The challenges ahead were clear. The vibrations experienced at high speeds would require damping solutions. The engine cooling system needed reinforcement for sustained high-power runs, and the propeller's thin blades, though revolutionary, demanded precision manufacturing that few plants could yet achieve. Yet despite these hurdles, the mood in the room was electric. By pushing the boundaries of design, Charles Sisk had done more than create a faster aircraft. He had rewritten the future of propeller-driven flight. What had begun as one engineer's risky experiment was now poised to change aerial warfare itself. As White later wrote in his flight log, "Today, we didn't just test a new propeller. We crossed into a new era of aviation." A total midday disintegration. Fighting against the violent shuddering of the airframe, White struggled to keep control long enough to attempt an emergency descent. His hands gripped the trembling control column as the Mustang bucked and twisted under the unbalanced forces tearing through its structure. For a few seconds, he managed to stabilize the aircraft's attitude, but the damage was spreading too fast. The nose section shook violently, and fragments of the engine cowling began to rip away in the airflow. From the ground, observers could see smoke and debris trailing behind the aircraft as it entered a steep, uncontrolled spiral. Sisk and the other engineers could only watch helplessly as a P-51H fell from the sky, its silver fuselage flashing in the afternoon sun before disappearing behind distant hills. Moments later, a dull explosion rolled across the test field, followed by a rising column of black smoke. The silence that followed felt heavier than the sound of the crash itself. Emergency crews raced to the impact site, but there was little left to recover. The aircraft had disintegrated on impact, scattering wreckage across the scrubland north of the airfield. It took nearly an hour before confirmation came through the radio. Robert White had not survived. The news hit the team like a physical blow. For weeks, White had risked his life proving the potential of Sisk's propeller, and now that same innovation had claimed him. Sisk stood motionless at the edge of the field as the recovery vehicles returned, their sirens echoing faintly in the distance. His mind replayed every design choice, every calculation, searching for the flaw that had led to disaster. The preliminary reports pointed to a classic fatigue failure. One blade had developed microscopic cracks at the base where manufacturing stresses had accumulated. Repeated high-temperature cycles and vibration had deepened the fractures until the metal could no longer endure the load. In the days that followed, investigators from Wright Field and North American Aviation pored over the wreckage. Metallurgical analysis confirmed what Sisk already suspected. The lightweight aluminum alloy that had made his propeller revolutionary also made it vulnerable to long-term fatigue when pushed beyond its limits. The thinner airfoil sections, though aerodynamically superior, provided less material to absorb stress concentrations at the hub junctions. The accident cast a long shadow over the Aeroproducts program. Military authorities immediately grounded all test flights involving the new propeller pending a full investigation. Colonel Bradley's terse directive arrived within hours. Suspend all operations. Conduct complete structural review before further testing. For Sisk, it was both a professional and personal tragedy. His design had proven its brilliance, but at a terrible cost. The very feature that had allowed the P-51H to break speed records had also introduced vulnerabilities invisible until it was too late. As he stood in the quiet of the now-empty hangar, the once-gleaming prototype reduced to fragments in his memory, he understood the paradox of innovation, that every breakthrough carries a shadow of its own risk. Yet even amid the grief and scrutiny, his conviction remained unshaken. The data recovered from the flight still told an undeniable truth. The concept worked. With refinement and stronger materials, it could redefine aviation once again. White's final flight had not been in vain. It had revealed a boundary that future engineers would learn to cross safely. And for Charles Sisk, that realization marked the beginning of a new, harder journey, one driven not by ambition alone, but by the solemn responsibility that every advance in flight demanded. Washington, his frustration barely contained. "We need reliability, not another laboratory experiment," he warned. For Sisk, every call felt like a verdict hanging over his life's work. Yet he refused to abandon the project. Beneath the exhaustion and grief, determination burned stronger than ever. The failure had not disproven his design. It had exposed the flaws in how it was built. That was something he could fix. Working late into the nights, Sisk and his small team began a methodical teardown of the Aeroproduct production process. They replaced batch-cast aluminum with precision-forged alloys, implemented ultrasonic inspection for hidden impurities, and introduced tighter heat treatment controls to prevent internal stress buildup. Each modification brought the design closer to the ideal balance between strength and performance that Sisk had envisioned. In parallel, he reinforced the propeller hub and introduced new bonding techniques at the blade roots, areas where microscopic fractures had previously formed. His guiding principle became simple. The propeller must not only perform but endure. Every improvement was tested, measured, and rechecked under punishing stress cycles designed to replicate the worst combat conditions imaginable. The same lightweight aerodynamic profile was retained, but the internal structure was now far stronger than before. By early February 1945, the first of the redesigned Aeroproduct propellers was ready. The new blades had a slightly thicker root section and a refined metal composition that improved fatigue resistance without adding significant weight. Even skeptics at Wright Field admitted that the engineering data looked promising. When the propeller underwent destructive testing in controlled laboratory conditions, it withstood more than twice the stress levels that had destroyed the previous model. Still, convincing the Army Air Forces to resume flight testing was another battle entirely. Colonel Bradley remained openly doubtful. "You can fix the metal," he said, "but can you fix the trust?" Sisk knew that only one thing would change minds: proof in the air. He requested authorization for a limited test series under closely monitored conditions. After weeks of debate and multiple technical reviews, permission was finally granted in March. The new trial began at Muroc Army Airfield, chosen for its wide desert expanses and isolation. The first test aircraft, a standard P-51D modified with the improved Aeroproduct propeller, were prepared under the strictest supervision. This time, every step was documented, every component double-checked. The test pilot, veteran flyer Captain James Potter, had reviewed the accident report in detail but volunteered without hesitation. "If this design works," he told Sisk, "it could save lives, not risk them." On the morning of March 10, 1945, under a cloudless California sky, the Mustang roared down the runway and lifted gracefully into the air. From the control tower, Sisk watched tensely as Porter climbed through 10,000 feet and began his evaluation. Minute by minute, telemetry data flowed in. Engine temperature stable, vibration minimal, performance consistent. At 20,000 feet, the aircraft reached 482 miles per hour in level flight, nearly matching the record speeds before the accident, but this time without a single sign of stress or instability. When Porter landed and climbed out of the cockpit, his expression said everything. "She's solid," he reported simply. "Smooth, powerful, and no vibration." The engineers around Sisk erupted in applause. For the first time since the December tragedy, hope replaced doubt. In the days that followed, Wright Field engineers confirmed the results. Fatigue tests showed no structural degradation even after prolonged stress cycles. Metallurgical scans found zero defects in the new alloy batches. The Aeroproduct propeller, once branded too fragile for war, was now stronger, safer, and faster than ever before. Sisk's persistence had transformed disaster into vindication. Though the war would end before the redesigned propeller saw full combat deployment, its legacy lived on. The innovations born from that turbulent winter would shape the next generation of aircraft propulsion, proving a timeless truth of engineering. Progress is built not just on success, but on the courage to rebuild after failure. "Ohio, either you fix this problem for good," Colonel Bradley warned, "or we're going back to Hamilton's standard propellers and ending this experiment for good." His words carried the weight of finality, but just when the project's cancellation seemed certain, Charles Sisk found an unexpected ally. Major General James Doolittle, both a combat hero and an engineer at heart, stepped in with crucial support when it mattered most. Doolittle's visit to North American aviation on January 8, 1945, came during the darkest period of the program. The general spent 3 hours examining the failed propeller blade, reviewing metallurgical findings, and listening carefully as Sisk explained the new manufacturing methods designed to prevent another disaster. "Charles," Doolittle said, standing beside him amid the rows of prototype parts, "I've seen enough combat to know there's no such thing as perfect safety in war. What matters is whether this propeller, properly built, gives our pilots a real advantage. And from what I see, it does." The data supported Doolittle's instinct beyond question. Months of tests proved that Sisk's design gave the Mustang unmatched speed and responsiveness. The challenge now was convincing cautious military procurement officials that these advantages outweighed the risks of adopting a redesigned propeller so late in the war. The solution came through a collaboration between Sisk's engineering team and North American's top manufacturing experts. They abandoned traditional aluminum casting, whose microscopic flaws had doomed the earlier blade, and switched to machining each propeller from solid billets of high-grade aircraft aluminum, pre-inspected with industrial X-rays. This new process was slower and costlier, tripling manufacturing time and nearly doubling expenses, but it guaranteed flawless structural integrity. Sisk also introduced a completely re-engineered hub system that distributed loads evenly, reducing stress concentrations that could cause cracks. For added safety, a secondary blade retention system ensured that even if a component failed mid-flight, the propeller would remain intact long enough for the pilot to land safely. By February 1945, the first of the redesigned propellers rolled out for testing. Test pilot Robert White, still recovering from the trauma of December's near-fatal failure, volunteered to fly the modified P-51H himself. His courage reassured everyone involved. As North American designer Edgar Schmude remarked during a meeting, if Bob White's willing to fly it again, it's ready for combat pilots. The results exceeded all expectations. With a new manufacturing process and reinforced hub in place, the P-51H consistently reached speeds of 492 miles per hour at 25,000 feet while maintaining the lightning-fast climb rate and agility of earlier prototypes. The vibration and heat issues that had once plagued the design were completely eliminated. By March 1945, production P-51H Mustangs began leaving the North American assembly lines, each fitted with Sisk-perfected Aeroproducts propeller. The timing was critical. Intelligence from Europe confirmed that Germany was rushing advanced fighters into service, including the Me-262 jet, an aircraft capable of outpacing most Allied planes. The new P-51H, however, restored the balance. At nearly 492 miles per hour, it could outrun any piston fighter in the Luftwaffe while still retaining its unmatched range and reliability, ideal for long-range escort missions deep into enemy territory. Lieutenant Colonel Paul Gunn, commanding fighter operations in the Pacific, was among the first to receive the upgraded Mustangs. After his first flight, he radioed back with excitement. "This isn't the same airplane we've been flying. It's faster than anything the Japanese have, climbs like a rocket, and still goes a distance with our bombers." The P-51HS combat debut in April 1945 confirmed those words. During bomber escort missions over Japan, its superior speed, climb, and maneuverability gave American pilots a tactical edge to strike first or disengage at will. With the Aeroproduct propeller, the Mustang had become the ultimate piston-engine fighter, unmatched in every respect. As production ramped up through the spring, the Army Air Forces planned to deploy nearly 1,500 of the new H-model Mustang for the expected invasion of Japan. The lightweight blades once dismissed as too fragile for war were now the beating heart of America's most advanced fighter. The war's sudden end in August 1945 came before the P-51H could be deployed in full numbers, but its legacy was already secure. Over 500 units saw combat, proving the design's worth across two major theaters. For Charles Sisk, it was a vindication of a lifetime, a reward for years of challenging accepted engineering wisdom. His fragile propeller had not only survived the brutal demands of war, but had powered the fastest piston-engine fighter the world had ever seen. Every turn of that propeller carried his signature, proof that innovation, once doubted and dismissed, had changed the course of aviation forever.